Hello everyone, my name is Hector Muñoz Gonzalez. I'm going to speak about this topic, which is called First Principle Study of the Effect of Pressure on the Physical Properties of layer carbide. This first principle study of layer carbide under hydrostatic pressure shows a phase transition from B3 to B1 phases at 23.5 gigapascals by calculating enthalpy and cohesive energy data. For the B3 phase, the calculated physical properties are consistent with the available theoretical data. Our phonons results show that this compound is stable at the pressure studied. Additionally, it is a metallic, anisotropic, paramagnetic, and brittle material with ionic-covalent bonds. As the pressure increases, the electronic flow surges around the carbon and lead atoms. The density of states extends. The hardness and the Young modulus increase becomes a ductile material with a tendency to metallic bonds. The optical results show that lead carbide is a promising material for application in the development of optical and optoelectronic devices. Introduction: Silicon carbide has been used as a coating material and a semiconductor in light and power electronics. Results from some studies carried out about 4-group carbides like germanium and tin carbide allows to identify potential technological application of this carbide in extreme environments, opening the possibility to find new carbides for similar application. This study focuses on describing the electronic, mechanical, vibrational, thermodynamical, and optical properties of the lead carbide under the effect of hydrostatic pressure within DFT frameworks using the GGA and PERT1 functional. This compound has not been possible to synthesize. However, theoretical results obtained by Wang and Ji described it as a metal and a B3 phase at 0 gigapascals. Computational details: the physical properties of layer carbide polytypes B1, B3, and Gursite phases were computed in the DFT framework using the CsCl code. The base set expansion was truncated to a cutoff kinetic energy of 500 electron volts. The Vanderbilt type ultrasoft pseudo potential were employed to represent the core electrons of the lead and carbon atoms. The electron-electron exchange correlation interaction were considered using GGA and the PW91 functional. The first build-one zone integration were performed using a 9 x 9 x 9 gigawatts on the Monk-Short back scheme. The converse tolerance were fixed as follows. The equilibrium force on atoms were less than 0.01 electron volts per Armstrong, and the ionic displacements in the highest strain amplitude were reduced to 5 x 9-3 Armstrong and 0.02 gigapascals respectively. The mechanical properties were obtained calculating the full tensor of second-order elastic constant using the method of homogeneous deformation. Besides, the phonon and optical properties were calculated using a cutoff energy of 820 electron volts and a billion set tested by 5 x 5 x gigahertz. The phonon dispersion curves were plotted using the data obtained from calculations under the DFT using the linear response method. With non-conserving pseudo-potential and a Q-vector creates spacing of 0.05 Armstrong-1. Finally, the optical properties were calculated with a plasma frequency of 10 electron volts for the polarization vector 100. This is our model. The lead carbide unit cell is shown as follows. On the left is the B1 phase, on center B3 phase, and the Gursite phase on the right. Parameters. In this table, we can see the lattice parameters calculated in comparison with theoretical and experimental carbide data for B1, B3, and Gursite phase at 0 gigapascals. And we can see the silicon carbide in theoretical and experimental data. the germanium carbide and tin carbide, we can see the theoretical date for B1 and B3 phases. Our calculation is the lead carbide and we can see a theoretical date for B3 phase. We can see the equation for the calculation of cohesive energy, Book's ratio, Poisson ratio, and Vickers-Gardner's. Results. On the top we can see the enthalpy energy. There are two phase transitions. From B3 to B1 at 23.5 gigapascales and the second from B3 to Bursita phase at 25 gigapascales. On the bottom there are the enthalpy difference. The B3 from B1 phase is more stable than B3 to Bursita phase. We can see at the top of this figure that the normalized lattice parameter and volume decrease as pressure increase. At the bottom, the lead bond length is greater than lead carbon bond length. At the B3 phase, as pressure increase, these bond lengths decrease, but at the phase transition there are a decrease of these bond lengths. At the B1 phase, as pressure increase, the bond lengths decrease. These are the density of state total and partial by atoms. At 0 gigapascales in the B3 phase, we can see a greater participation near of the Fermi energy of carbon 2p orbitals in the valence band. In the conduction bands, there are a greater contribution of lead 6p orbitals. As pressure increases, the density of state disperses. After the phase transition, at 23.5 gigapascales in the B1 phase, we can see a greater participation of states close to the Fermi energy, in special by carbon 2p orbitals. As pressure increases, the density of states disperses again. It's shown that as pressure increases, the cohesive energy decreases. There is an abrupt decrease at the phase transition, from B3 to B1 phase. Mechanical properties. On the top is shown the elastic constant. As pressure increases, the constant increases. The C11 constant is greater than C12 and C44. In the phase transition from B3 to B1 phases, the C11 and C44 constant increase, but C11 decrease. But after that, the elastic constant increase. On the bottom of this figure, we can see the bulk, shear, and Young's moduli. At 0 gigapascales in the B3 phase, the Young's module is greater than bulk and shear module. As pressure increases, the bulk module is greater than Young and shear moduli. In the phase transition, the Young's module is greater than the others moduli. In the B1 phase, as pressure increases, the moduli increase. On the top, we can see that the Book's ratio, as pressure increases, this decrease, but the Poisson ratio increase. In the phase transition, the Book's ratio increase, but the Poisson ratio decrease. In the B1 phase, the Book's ratio decrease and the Poisson ratio increase. On the bottom of this figure, in the B3 phase, as pressure increase, the Vickers hardness decrease. In the phase transition, this property increase. After this pressure in the B1 phase, there is a slightly decrease in the Vickers hardness. Vibrational properties. In these figures, no negative frequencies are shown. At 0 gigapascals in B3 phase, carbon atoms vibration are located at high frequencies, and the lead vibration in low frequencies. As pressure increases, the vibrational gap between carbon and lead vibration increases, and the phonon density disperses. Thermodynamic properties. As temperature increases, the entropy and enthalpy increase, but as pressure increases, the entropy and enthalpy decrease. On the other hand, as temperature increases, the Helmholtz free energy decreases, but as pressure increases, the Helmholtz free energy increases. Optical properties. Absorption. There is absorption in low frequencies in the UV region, followed by infrared and visible region. As pressure increases, the values of this property increase. Reflectivity, refractive index, real and imaginary part. The values of these properties is greater in the infrared and visible region, followed by low frequencies in the UV region. And as pressure increases, these values increase. Conductivity, real and imaginary part. The values of these properties are greater in the infrared region, followed by low frequencies of UV. As pressure increases, these values increase. Conclusions. At 0 gigapascals, the most thermodynamically stable structure is the B3 phase. The lead carbide is a metallic and anisotropic material with paramagnetic behavior, which is energetic, mechanic, and dynamically stable. It performs a phase transition at 23.5 gigapascals from B3 to B1 phase. By applying pressure, the volume and bond length decrease, causing an increase in the electronic flows near of atoms. The density of states dispersed. There are greater participation of carbon 2p and lead 6p orbitals, and a possible separation of the crystalline phase. There is a conversion from a brittle material with ionic-covalent bonds and good hardness around 13 into a ductile material with metallic bonds tendency and increase in hardness and Young's moduli. As the pressure value increases, the density and the anisotropic of lead carbide were increased. However, above phase transition, the anisotropy decreased due to the deformation along the 100 direction. The higher frequencies are associated to the carbon atoms, whereas the lower frequencies to the lead atoms. As the pressure increases, the frequencies disperses, increasing the phonon gap between atoms vibration. At high temperatures, entropy and enthalpy increase, but the Helmholtz free energy decreases. As pressure increases, entropy decreases, but above the phase transitions it increases slightly. Enthalpy decreases due to the volume decrease, and Helmholtz free energy increases. The lead carbide is a promising material for application in developing optical and optoelectronic devices at infrared, visible, and UV low frequencies regions. The lead carbide has associated the peculiarity that as the pressure increases is less photoconductivity in the visible and the infrared regions, but the photoconductivity increases at lower frequencies in the UV region. This work was partially supported by the project IPN-SIP and the UNAM de Gapapapit. Escamilla and Muñoz acknowledged the scholarship granted by CONACYT and BEFI IPN. Cervantes acknowledged the postdoctoral scholarship granted by CONACYT. Antonio acknowledged the postdoctoral scholarship granted by the GAPA, and calculations were done using resources from the Supercomputing Center de GETIC UNAM. These are the reference used. Thanks for your attention. For more information, this is the DOI and the email contact.